Hey, good morning or afternoon to you all. It's Thursday, and as you remember, today we've got a quiz. So what's going to happen is we're going to pass out quiz number one, and we're going to give you about 20 minutes to work on this. We'll try to give you an alert when there's about 2 minutes left, and then you can pause this tape. And when you guys are done, then you can start it back up again. So let me pray for you guys, because I think this is the first quiz or test we've done in this class yet. So let me just pray for you guys and just give this time to the Lord. Father, thank you again for an opportunity to glorify you with our mind, to give you praise and to be amazed at this amazing world that you've created, and to see these tools that you've given us to be able to understand it. Lord, help these students as they're taking this quiz. Lord, calm their nerves. Help them to remember the things that you've shown them, that they've learned up through this past week and a half, 2 weeks. And would you just give them clarity of thought as they're taking their quiz today? In Jesus' name, amen. So you can pause this here, and then we'll pick right back up with you with the lecture after the quiz is done. Okay, so what we're going to do today, next week, if you actually look at the schedule, next week we've got an exam. Monday is set for review for that exam, so I'm going to go back through kind of broad stroke, the stuff that we've covered up to this point. There's a fair amount, but I'm going to try to refine it down so you kind of have an idea of the types of questions I might ask on the test. And then Wednesday, you've got a homework that's due. So I'll be able to answer any questions that you have on that homework on Monday, and we'll have the full time on Wednesday to be able to take that exam. So, and I will have the quizzes graded by Monday as well. So you'll have those quizzes back. So you'll have two homeworks back, and then you'll also have that quiz back. So you'll have some things to study from as well. Okay, so the plan for today is to look at two things. We looked at logs last time, and again, if that was somewhat confusing, that's okay. We'll go back through some of that on Monday if you've got some more questions. But the whole idea of inverses, again, is this idea that we want to solve equations. And in order to solve equations, in order to pull things off of x, we've got to apply inverse functions that dissolve them. So if you want to think of if I've got x and I've got a function applied to x, the way that I dissolve this function is to apply the inverse function, and it dissolves it. Okay? So we've got our basic functions like x to the x squared, x cubed, x to the fourth, 1 over x, 1 over x squared, 1 over x cubed, square root, cube root, absolute value. You've got your exponentials and your trig functions. Maybe we can just draw those here. So we've got functions like x squared, x cubed, x to the n, 1 over x, 1 over x squared, 1 over x cubed. Okay, we've got square root, cube root. These are all functions that you should be able to draw. Absolute value of x. And then we had exponentials, right? And then we had trig functions, right? Our sine, our cosine, and our tangent. Those three you should be able to draw by memory now. So you should not have any trouble with those. Now remember, these root functions are the inverses of these power functions. And then we looked at, well, what's the inverse of exponential functions? Those are the log functions. Those look like this. So what we're going to do today, we've kind of got one last class of functions that we don't know how to take inverses of. So we're going to figure out what are the inverses to these trig functions. So that's the first thing we're going to do today. We'll hopefully spend about 20 minutes or so, 30 minutes doing that. And then we'll spend the last few minutes of the class talking about how do you shift these functions around now, okay? So that's kind of the plan. So we're going to start with these trig functions. And to do that, we are going to need to draw them. So let's start with the function sine. And what we're going to do to find the inverses of these functions, we're going to do it graphically first. And then we're going to look at it algebraically, and we're going to try to solve a couple things. So that'll be our plan for sine, cosine, and tangent. So let's start with sine. Take a minute, draw the sine function. If you can't draw the sine function, you got to get that index card out, because this could be an exam question. Okay, what you should do should just take like 5 seconds. Should look something like this. Now I'm going to try to be a little more precise with this, because we're going to be drawing, and I want it to look nice. So remember, this peaks at pi over 2, it peaks up at 1, and then over here at negative pi over 2, it goes down to negative 1. Now, the first thing that I want to ask you is, if I try to get an inverse to this, is there going to be a problem? So I want you to think, if I were to draw on that line y equals x and flip this, you can kind of see that what's going to happen is that instead of going off, let's tilt your head, instead of going off to the right, this goes off to the left. Instead of going off to the left down here, this is going to go off to the right. Okay, now what do you immediately notice about that green thing? Not a function. Okay, so which means that the original thing failed the horizontal line test, which we can see, which also means it's not 1-to-1. That's the name that we give. If you pass the horizontal line test, you're 1-to-1. If you don't pass the horizontal line test, you're not 1-to-1. So what we're going to need to do, remember when we had x squared and that didn't pass the horizontal line test, we cut it, we restricted the domain so that it did, and then that'll end up working. So let's try that. I'm going to redraw sine again. And we're going to cut it, and just like with x squared, there's multiple ways that I could cut this, but there's kind of a standard way to cut it. Like with x squared, when we had x squared, the way that I cut this so that I would have one function that is 1-to-1, I would cut off this other part and I would use this piece right here, right? That's kind of the standard one, and you'd get the inverse function would be square root, which is kind of the standard inverse. So here for sine, this is the function sine. So pi over 2 and 1. Negative 1 at negative pi over 2. What I'm going to do is I'm going to cut it right here and right here. I'm going to sort of chop it and get rid of all this stuff. That makes sense? So I'm going to cut it at negative pi over 2 and pi over 2, and then delete the rest of this equation, of this function, the graph of this function right here, okay? So that's my new, I've kind of cut it right there, and that's my sine function. And the domain, I'm restricting that domain to negative pi over 2 to pi over 2. Okay? So now let's try getting an inverse function. And what's going to happen if we do this is, again, instead of going off to the right, this one goes off to the left. And instead of, let's kind of Instead of going off to the left, this one goes off to the right. Okay? So what I get, I'm going to draw it down here just so there isn't, because there's a lot of stuff on this graph. Now the question is, how high up and how far down does it go, and then how far left and right? Well, if you remember, inputs become outputs, and outputs become inputs. So these inputs, from negative pi over 2 to pi over 2, become the y values. So the biggest y value for this inverse is pi over 2, and the smallest y value is negative pi over 2. So the inputs become the outputs. And then the outputs, the original function goes from negative 1 to 1, so the domain, the x values are now going to go from negative 1 to 1. So this is the inverse function for sine. And we're going to use a couple of different ways to write this. So we're going to call this function sine inverse of x. Looks like sine to the negative 1. We're also going to call it arc sine of x. Arc sine of x. Now don't ask why it's called arc sine. That's a different story completely. We're not going to get into that. But the word arc sine just means inverse of sine. Part of the reason that we're going to use arc sine instead of sine to the negative 1 is that the inverse function, if you remember, the inverse function is not 1 over. But we tend to get confused by that negative 1 in the power. So instead of writing sine to the negative 1, which is going to get confusing, generally we're not going to write that. We're going to write arc sine. Okay? So this function is the function arc sine. And the domain is from negative 1 to 1. Okay? So again, one tip here, kind of like what we were doing with logs, is if I'm trying to evaluate an arc, like arc sine, it's best to undo the question and rewrite it. Okay, so let me take an example here. Just like if I did log base 2 of 8, what does that mean? I'm going to ask that same type of question here. If I say arc sine of 1, what does that mean? Well, what it means is what angle, when I take the sine of it, do I get 1? So I have to think about my unit triangle. If I take the sine of an angle, and I get 1, well, sine is the y part. That means this has to be pi over 2. So the answer to this problem is pi over 2. Remember, it's just like that cube root. If I say, what's the cube root of 8? You're thinking, okay, what cubed is 8? Because I don't understand cube roots. So 2 cubed is 8, so the answer is 2. Same thing here. Let me give you another example. Arc sine of 0. What this means is the sine of what is 0. And again, we're thinking sine is my y values. So that means that this angle has to be 0. So the answer to this is 0. And you can see this arc sine function, when you plug in 0, you get 0. That makes sense. That's the way it should work. Okay? Let's do one more. Arc sine of 1/2. What does this mean? Well, it means that the sine of what is 1/2. Now again, you have to think of your unit circle in that triangle. The y value, the y part is going to be 1/2 when this angle right here is 30 degrees, or pi over 6. So the answer to this question is pi over 6. Okay, so when you're evaluating these inverse trig functions, you must unravel the question so that it makes more sense using a trig function. For instance, if I were to say, what's the arc sine of 10? If you understand what's going on here, you can easily see that this is a really bad question. Because what this is asking is, sine of what is 10? Well, you can't take the sine of anything and get 10, right? Sine goes between negative 1 and 1. You can't ever get anything outside of negative 1 and 1. So this is a bad question. So this does not have an answer. 10 is not in the domain. That's why this domain is between negative 1. Okay? So that is the arc sine function. Hopefully that makes sense. Let's go on to the arc cosine function. Okay, the inverse of cosine. So let's draw a cosine. I could stop and say, hey, draw a cosine. But I'm going to go ahead and proceed here. So remember, cosine starts at 1. Cosine is the x part. And the x part with this unit circle, the x part starts with 1. And once you start with 1, you have to go down. So here is cosine. That is my cosine function. And again, so this is cosine x. Again, if I were to draw in that line y equals x, one of the things that you notice is that, okay, this is going off to the right, so this has to go, well, this has to go off to the left like that. Okay, so we're supposed to mirror, it's kind of not that great, but okay. That's what happens if I take this and flip it around that line, I get something like that. And the one thing I want you to notice here, function. So again, just like with our friend sine, we're going to have to restrict the domain. We're going to have to cut this function. Notice I can't cut it between negative pi over 2 and pi over 2 because that's still not 1 to 1. If I were to flip that, I get this part. That doesn't pass the vertical line test. So where I'm going to cut it, I'll redraw it here, but where I'm going to cut it is I'm actually going to cut it right along here. And in this piece, it will pass the horizontal line test, so when I flip it, it's going to pass the vertical line test. So let's draw cosine again. Okay. This is cosine. Okay. And then again, what I'm going to do is I'm going to cut it right here from 0 to pi, and I'm going to cut out the rest of this stuff here. So we're going to erase this essentially, and I'm going to cut it right here. Okay, so that is my function. Let's draw in our y equals x. And let's flip it, and what we're going to get is something that looks like this. It looks a little bit like the arc sine function, but it's kind of shifted up and it's flipped around. Okay? So the resulting thing starts here and goes up to here. Now again, we're going to ask these questions. Where does it go from and to on both sides? So you want to think about this. At 0, the cosine function is 1. Down here, it's negative 1. And it crosses at pi over 2. So x has become y's. So this is going from 0 to pi. And it crosses at pi over 2. And then the y's become x's. So this is going from negative 1 to 1. Okay. This is the inverse function for cosine. We call this cosine inverse of x. But again, we get confused with that exponent, so the other name that we give this is arc cosine of x. Okay? Arc cosine of x. So, again, the idea here, if I want to evaluate numbers, if I were to give you a question like, you know, what is the arc cosine of 1? What I want you to think about is, this is asking the cosine of what is 1? And the answer to that, if I were to say, well, where's the cosine 1? Cosine is the x part in my unit circle. So that's 1 when that angle is 0. So the answer here is 0, and the arc cosine of 1 is 0. If I were to say, what is the arc cosine of 0? Well, what that means is, when is the cosine 0? And I think about my x value is 0 when my triangle goes up like that, and so the angle is pi over 2 here, so this has to be pi over 2. And you can see that in this graph here. Okay? So when you're evaluating, again, I'll continue to emphasize this, when you're evaluating these inverse functions, you must always unwrap what they mean so that you truly understand what's being asked, and then you can answer the question. Okay? Any questions that you can ask virtually? Give you a second to just catch your breath. We've got one more function here. Okay. And that is, if I find my eraser here, tangent. And everybody always freaks out with tangent. Tangent, if you remember, tangent is this crazy one with a bunch of vertical asymptotes. Right? Tangent looks like this. Okay, so this is tangent. Okay. So, how do we get an inverse function for this? Okay, well, again, let's do just kind of like we did with our sine function or our cosine function. If we just kind of graphically tried to find the inverse function, we didn't care about one-to-one or not or whatever, what would happen here is kind of crazy, but what you can kind of see that what's going to happen is this piece is going to kind of go off this way instead. And then instead of a vertical asymptote, we're going to get this horizontal line. And again, you're going to get another one of these. And another one of them. So this is just crazy, right? This green thing is actually a big, big, big mess. But you can see, again, the green stuff is not a function because the original thing was not one-to-one. So what we're going to do instead is we're going to have to cut it. And you can probably guess, maybe, based on the picture, where I'm going to cut this. Okay. What I'm going to do is I'm going to just not draw the rest of the function of the tangent function. So I'm only going to draw the part from negative pi over 2 to pi over 2. Okay, and you'll notice this part does pass the horizontal line test. So when I flip it, it's going to pass the vertical line test. Okay, so let's do that flipping. There's my line y equals x. And what I get when I do this flipping is something that does this. And those horizontal lines become vertical lines. So let's redraw that green thing. So that is the inverse function for tangent. And it goes from, just like the x values here went from negative pi over 2 to pi over 2, the y values now go from negative pi over 2 to pi over 2. Notice that the range here is all real numbers, so the domain here is going to be all real numbers. Okay, so this is an important thing to notice. This is a nice function in that you can plug anything in that you want. And we're going to call this function arctangent. Okay, that is our arctangent function. Okay, so those three functions, believe it or not, arcsine and arccosine don't actually come up that much in calculus. They do come up some. Arctangent comes up surprisingly more, which is maybe seems a little mysterious, but this function will come up more than other functions will. these three functions you need to add to your basic function list as well. So we had our powers and 1 over powers of x, our roots, absolute value, exponentials and logs, and now we have trigs, and now we have inverse trig functions. Okay? So these you need to make sure that you add to that list. Okay? What we're going to do here is we're going to take a 5-minute break, and we're going to come back and we're going to talk a little bit about transformations, about moving functions around. And then that'll be it for the kind of review of the material you probably should have seen up to this point. Monday we'll do our review. Wednesday we'll have our exam. And Thursday we'll start actual calculus material. So take a 5-minute break, come back. You can pause this, and we'll get going with transformations. Okay, let's talk about transformations. What I mean by transformations is moving functions around. Okay, so we're going to be taking functions and moving functions around. And what this will do is this will actually allow us, once we have our basic functions, we can take those and move them around and be able to graph a lot more types of functions than just the ones that we have here on our basic function list. Okay? So let me explain, I'll just show you what I mean by moving things around. So let's first take examples of horizontal and vertical shifting. So there's actually three kinds of movements that we're going to look at in this. The first one is horizontal and vertical shifting. So let's take an example. Let's take the function x squared. So take a second to draw that. You should be able to go and yep. So now the question is, what happens if I write, so this function there, that's not too great, but that's okay. What happens if I look at x squared plus 3? What does that do? Well, you can think of, if you kind of really just forget, if we were to plug in 0, we'd get 3. If we were to plug in 1, we'd get 4. If we plugged in -1, we'd get 4. So what happens is that this function is just this function shifted how? So this got shifted up 3. How do you think I would shift this down 2? Let's just say I wanted it to go down to, what should I do? What do you think? Tell the person next to you what you should do. I probably want the function x squared minus 2. Okay, and if we were to plot a few points, you would pretty easily see that this is just the x squared function brought down to, okay? So if I add something to the outside of x squared, that shifts me up. If I subtract something, that shifts me down. Okay, that gives me vertical movement. How am I going to get horizontal movement? Okay, and the way that I'm going to do that is, let's take an example here. Let's graph x minus 3 quantity squared. So in effect, what I'm doing, well, let's do x plus 3 first, okay? Because I think this will make more sense if I kind of pair these together. So I want you to think of, let's just think about just kind of random plugging in points just for a second. If I were to plug in 0, I suddenly get a big number, I get 9, right? I don't like big numbers, and if I start plugging in positive numbers, I'm going to get even bigger numbers. So let's start going negative. If I plug in -1, -1 plus 3 gives me 2 squared is 4. If I plug in -2, -2 plus 3 is 1, squared is 1. If I plug in -3, I get 0, and if I plug in -4, I get 1 again. So this is what I get. So what happened? This one shifted left 3. Now that might surprise you. You might have thought adding 3 on the outside shifted me vertically, in a positive direction by 3. So adding 3 on the inside should shift me in a positive direction. But it actually shifted you the other way. I'm going to say more about that in just a second. Okay, what if I wanted to go to the right 3? I actually did want to go to the right 3. What do you think my function would be here? Okay, it's going to be x minus 3 squared. That's going to shift me to the right 3. Okay, so the rule here is as follows. If you want to shift vertically, then you add or subtract on the outside. Okay, adding does what you would expect it to do. It causes you to go up, and subtracting causes you to go down. Okay. But if you want horizontal movement, that corresponds with the inside. And the inside, you're going to see, we're going to do this in several different ways. The inside always does the opposite of your intuition. So, whereas on the outside, if you add, you expect to go up, and if you subtract, you expect to go down. When you do this on the inside, it actually is the opposite of your intuition. So when you add, you expect to go right. You're right. It turns out you actually go left. And when you subtract, you don't go left, you go right. Okay, so adding, instead of causing you to go positive, it's the opposite of your intuition. Negative causes you to go forward. So this is the opposite of your intuition. Okay? So adding or subtracting on the outside has vertical movement. Adding or subtracting on the inside has horizontal movement. So let's try another example here. Okay. Let's try. We'll do kind of an interesting example. Let's take the function x. What does that look like? That looks like this. Okay. And now let's add 5 to the outside. What is that going to do? That should shift it up 5. So you should see something like this. Okay. If I instead subtracted, let's do x minus 4. What is that going to do? Yeah, that's going to shift it down 4. Now, do you notice anything? One thing you might notice is that you could think of this as going up 5. You could also think of it as going left 5, which actually corresponds. If we're adding, we go left. If we're subtracting, we go right. So that does actually match our intuition here. Okay. Now these are functions, x plus 5 and x minus 4. I would expect you to be able to graph those anyway, but just kind of shows you how these transformations work. Okay. Let's try one more. Let's try the function 3 to the x. Fun. Okay, Okay, take a second and graph that function. Okay, what you should have should look like that, right? It goes through the point 0, 1. Now, here's what I want you to try to do. Graph 3 to the x plus 2 and 3 to the x minus 1. Let's figure out what these look like. So if I add 2 on the outside, what that's supposed to do is shift me up by 2. So what's going to happen to this function, it was going through 0, 1, now it's going to go through 0, 3. And instead of approaching the x-axis, it's going to approach a line that's 2 up from the x-axis. So it's actually going to approach that line. So this function, 3 to the x plus 2, should look like the function 3 to the x just shifted up 2. If I did 3 to the x minus 1, that's going to be my 3 to the x function, but I'm shifting down 1, so it's going to approach that line right there, and it's going to go through 0, 0 instead of 0, 1. Okay, that'll be my function 3 to the x minus 1. What about if I had 3 to the x minus 1? How is that going to be different? How is this function going to be different? There I'm subtracting 1 on the inside, so it's not going to be vertical movement, it's going to be horizontal movement. So I've got my function kind of like this. Am I going to go right or left? I'm actually going to go to the right. Again, subtraction, we'd think go down negative, but it actually forces you to go positive. It's the opposite of your intuition. So this function would be this function, just shifted a little bit, so that instead of going through this point, it's going to go through this point, but it's still going to hug the x-axis like that. Okay? Does that kind of make sense, shifting horizontally and vertically? Okay. The next group of functions, or the next way that I can move or change functions around, we're going to do stretching and compressing. Okay, stretching and compressing. So stretching and compressing, what happens here, let's take as an example, let's take our function sine. Graph that. Okay. Let's say that I gave you the function 3 times the sine of x. Okay, 3 times the sine of x. Now the fact that I'm doing something to the outside of this function should tell you that I'm going to do something vertically. Okay, if we were to graph this function, what we would find is if we plugged in, let's plug in a few values. If I plug in 0, just like here, I'm going to get 0. If I plug in pi over 2, before I got 1, now I'm going to get 3. If I plug in pi, I'm going to get 0. If I plug in 3 pi over 2, instead of negative 1, I'm multiplying by 3, so I'm going to get negative 3. So you can kind of see what's going to happen here is it's a similar function. So what happened? We took it, we stretched it by a factor of 3. Okay? So we stretched vertically by a factor of 3. So anything that was 1 became 3. Anything that was 2 would become 6. Now you don't have anything 2 here, but anything that was 10 would become 30. So it's like, imagine this thing with rubber and you just stretched it like that. Okay, whereas kind of the opposite of that would be if I divided by 3 or if I multiplied by 1/3, if I had 1/3 sign, then instead of looking like this, the highest point instead of being 1 is actually going to be 1/3. So it's going to compress this function so that it's 1/3 of the amplitude of what it was before. Okay? So this compresses vertically by 3. Okay? Make sense? So multiplying on the outside stretches, dividing on the outside compresses. What do you think happens on the inside? If I were to do this on the inside, what would happen? What do you think would happen? Let's give it a try and see. Okay, let's try the sine of 2x and see what happens. So if I plug in 0, I'm taking the sine of 0, which is 0. But now if I plug in pi over 2, which was right here before, 2 times pi over 2 is pi, so what I'm actually taking the sine of is the angle pi. And the sine of the angle pi, that's the y part here, that's actually 0. So what you can kind of see is this pi over 2 part actually took on the characteristic that the pi had. So what's going to happen here, if I were to plug in pi over 4 times 2 is pi over 2, and that's where the peak is going to be. So the peak is still at 1 and -1, but it just goes twice as fast. So in other words, this is compressed. You can kind of see I took this graph and just compressed it horizontally by a factor of 2. So this is compressed horizontally by a factor of 2. Now, I could predict that it's going to be horizontal because I'm doing stuff to the inside. When I multiply, I usually think stretch. Inside is the opposite of my intuition, so it's going to compress. If I divide on the inside, as you can probably guess, what this is going to do is this is actually going to stretch horizontally. So instead of pi over 2, and pi, instead of seeing a wave like that, I'm actually going to see something that is going to take a much longer time to, so I stretch it out. This is stretched horizontally. By 2. Okay, does that make sense? Okay, so yeah. So shifting is by adding and subtracting. Outside is vertical, inside is horizontal. Stretching and compressing. Okay, again, outside is vertical movement, inside is horizontal movement. If I multiply by something like 3, okay, on the outside, so multiplying stretches, and then dividing compresses. Horizontally, that works the other way around. So if I multiply by something on the inside, by a number bigger than 1, that's going to compress. And if I divide by something on the inside, that's going to stretch. Okay? Makes sense? Okay. Let's do an example here. Well, let's do one more type of movement. So the last type of movement is reflecting. And the way that we reflect is we multiply by a negative on the outside or the inside. So let's again take the function, let's take the function x squared just for a second. If I multiply by a negative, so if I look at the function negative x squared, if I multiply by a negative on the outside, if you were to graph that, it looks like this. Now what happened? I reflected vertically. And again, I'm doing something on the outside, so because I'm doing something on the outside, I would expect things to happen vertically. And so when I'm multiplying by a negative, it's going to reflect it vertically. Same thing if I had like the function, for example, sine of x. If I took the negative of that, what I'm doing is I'm just reflecting this around the x-axis. So everything that was positive becomes negative, and everything that was negative becomes positive. So it just flips the graph around the x-axis. So it reflects vertically. Okay. What do you think is going to happen if I multiply by a negative on the inside? It's going to reflect horizontally. So what's going to happen in this case here with x squared? If I multiply by a negative on the inside, well, if I reflect this horizontally, if I go like this, it's the same function, and that should make sense, right? Because if I multiply by a negative on the inside, you square it so it doesn't matter. Right? Over here, if I take the sine function and I put a negative on the inside, what that means is I'm going to flip it horizontally, but you'll actually notice that that ends up looking actually exactly like this function. Okay. And this leads me to one last definition here. Let's just mark up here that for reflections, if I multiply by -1 on the outside, that reflects vertically around the x-axis. If I multiply by a -1 on the inside of a function, that reflects horizontally. And for some special functions, like x squared, if I put a negative on the outside, that doesn't change the function. Okay? If I put a negative, let's try this again. If I put a negative on the inside, that doesn't change the function. Like, for instance, x squared. X squared, negative on the inside doesn't change the function. That means that if I flip around the y-axis, nothing changes. We call these kinds of functions even functions. I don't know if you've heard that term before. But x is an even power of x, so when I plug in a negative, that negative is going to go away. So we call that an even function of x. Okay, the other side of that is that if you plug in a negative, and you get the negative of the original function, then we say f is odd. Okay, so for example, if I take the function x cubed and I plug in a negative, notice that that's the same thing. 3 negatives give me a negative. So that's the same thing as the original function. Now what this means graphically, actually, is that if you take x cubed, all odd functions look the same when you flip them like this. I'm sorry, all even functions look the same when you flip them like this. All odd functions look the same when you turn your head upside down like that. Okay, so x cubed is an odd function, so if I turn my head, it'll look good. Now, not all functions are either even or odd. You can have neither. But if you have an even or an odd function, it has some special properties. So I don't know if you've seen that before. That won't come up that often either, but it's useful in certain contexts. So I think that's it. Yeah. So if you've got extra time, I'm not sure exactly how classes proceeded here, but if you've got extra time, you can take a look at the homework for Monday. We'll answer questions on that on Monday, but it's not due until Wednesday. Okay? So you guys have a great weekend. Study hard, relax. Try to do both at the same, maybe not at the same time, I don't know. But I'll see you guys on Monday. Thanks so much.